Hi, everybody, and welcome. This is Mr. Polly, and welcome to our last unit, Chapter 11 of the year 2015-2016. We're going to talk about the blinding aspects of light. We're going to talk about frequency, wavelength, that was misspelled there. We're going to talk about energy, what light travels through, that there's more than visible light, and other types of electromagnetic radiation. I'm going to use electromagnetic radiation as the abbreviation of EM. I think I'd write that down about 100 times because every time I saw EM, I'm like, what's that? Electromagnetic radiation. And this is kind of the key. We're going to talk about spectroscopy in this unit. So how we can use these different types of light and energy to make it work. Light is a wave, whoa, and a particle. It is weird as both. It is whatever we want it to be, which is weird. So we use the aspect of its particality, there you go, when we want to, and we use the aspects of its wave nature when we want it to as well. So, for example, waves bend around corners. And we know that light bends around corners, right? And it's a particle because it is an exact amount of energy called a photon. So it has little bundles of energy. Those bundles are photons, and they are in all or nothing groups called a quanta or a quantum. And what this means is I've got a photon that's that big, or I have a photon that is that big. Notice they're different sizes. You can't make this one a little bit more. You can't add little bits of energy and have it grow from part to part to part. It's an all or nothing kind of thing, like a person. Yeah. Light can also be a wave. So there are parts of a wave. This is what a wave looks like. In math class, there's sine waves and cosine waves and all that other stuff that goes on with it. You know the parts of a wave are a wavelength, right? Now the frequency of a wave. Now imagine if I have my hand is right here. Oh, good, Mr. Foley Art. Here's my hand, and I'm pushing on it. And if I'm pushing on it slowly, it would go. And if I push on it quicker, it would be. So that would be the speed that it goes. Okay. Those number of times that I hit the wall over here would be the frequency. How often do I hit a peak? Bam, 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 or bam, 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 bam. Frequency can be changed by changing the speed. Now that doesn't happen for us because everything moves at the speed of light, or if the wavelength changes. So if you think of if I'm pushing them at the same speed and I have something that looks like this, if I'm pushing them at the same speed, it would be bam, 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 bam. Same speed, bam, bam, bam. So see how frequency is different. And frequency also impacts the amount of energy that we have. All electromagnetic waves move at the same speed. Okay. So lambda is the distance from, this is called a crest, the crest, right? So the crest is the top of the wave. Lambda is the wavelength, so that's the distance from crest to crest. And frequency, you can't use the word frequency, but essentially it is how often, it doesn't have to be the crest particularly, the crests pass. And then just in case I mention it, we talked about this being a crest. This is called a trough, like what pigs eat out of. If you know what pigs eat out of, your life is much sadder than you think. The energy of light can be calculated. So it means we can calculate the energy. We can also calculate the frequency. Oh my goodness, that's a symbol for frequency. And we can calculate the wavelength. Oh, that's wavelength. So see how this, it's really the Greek letter nu is frequency, and lambda is the wavelength. So E equals h nu. H is Planck's constant. And you guys don't like constants. Constants are like pi. You know, you just throw pi into an equation, you get the right answer. It's really kind of sort of the slope of a line. And that's determined by graphing. Remember, all these equations come from graphing. Frequency equals the speed of light divided by wavelength. Okay, so the speed of light is 3e negative 8, and that's a constant again. It's like pi. Okay, only the speed of light makes much more sense to us. The wavelength of visible light is 800 nanometers. Find the energy of a photon. So if I have 800 nanometers, so the first thing you have to do is change to meters. Nanometers is the only conversion you might have to do. And you don't have to do any. But this one's on here, and it's so common, I wanted to show you at least one. I want to cancel nanometers and go into meters. Well, 1 meter equals a millionth of a nanometer. This is way back in chapter 1. Ooh, chapter 1, I remember you fondly. Ah, so 800 divided by 1e negative 9. Oops, 800 divided by 1e negative 9. I just use a calculator to divide by 1. And that is 8e11 meters. Okay, so that's my wavelength. I want to find the energy. Now, the first thing I do when I'm trying to do math is I browse my equation sheet. E equals h nu. Remember, this is frequency. Well, frequency is not wavelength. So I now need something with wavelength. I had an equation with that, didn't I? Oh, nu equals c over lambda. Nu equals c over lambda. Hey, that's lambda equals c over lambda. So nu, oh come on, nu equals 3e8, speed of light, over my new lambda, which is 8e11, and that'll be my frequency. Oh, I have no idea why that's coming and going. 3e8 divided by 8e11 is, so my new is 3.75 negative 4. Okay, so now I'm going to use this equation. E equals Planck's constant times lambda. So H, oh, I forgot it. 6.63 E negative 34. 6.63 E negative 34 times my frequency, which is 3.75 E negative 4. I get my energy. And because I kept my stuff in meters, I get the right answer too. 6.63 E negative 34 times 3.75 E negative 4 is 2.49 E negative 37 joules. Just to make sure my units are right, let's see what Planck's constant's energy unit is. Oh, kilogram meter per second, that is a joule. No. Ah, where'd you go? It was 2.49 negative 37 joules. So that energy comes out in joules. It's always more in meters and seconds. Electromagnetic EM waves do not need a medium. Sound needs a medium. We hear sound because it pushes the air. Sound can also push water. Sound can also push rocks. Electromagnetic waves can travel through empty space. Sound is not electromagnetic radiation. Okay? So you know it does not need a medium. So that's how it gets from here's the sun. You are my sunshine, my only sunshine. Here's the earth. I don't know what that is, but anyway, there's nothing in between here and it can travel through this. Okay? Like fish need water to swim through, they need a medium. Electromagnetic radiation does not. Light can be separated into smaller colors called a spectrum. Electrons jump and fall energy levels and emit or absorb light. So we can prove this spectrum. I can shoot white light in here, and a prism comes out with a rainbow of fruit flavors. Here's the Skittles. Yay! So electrons fall and jump. So if you see this, if I have a hot gas and I heat it up, right, and pass it through a prism, what happens is I see distinct lines. Okay, so we can identify atoms by this jumping of electrons. Notice when an electron was at level 4, it falls all the way down to level 2. It'll emit light right here. And if electron falls from 4 to 2, this atom will emit one of 2 bands of light right there. And if it's just a 3 to a 2, it emits it right here. Okay. So to draw that a little bit better, if I have an electron right here and it falls down to here, we'll call this lots of energy. And if this one falls from here down to here, we'll call this little energy. And lots of energy would have a shorter wavelength. Okay. Now here, the same thing can happen if I have an electron here and I add energy to it. Here, have some energy. Woo! This one will absorb lots. Okay, so do you see how this one said lots of energy, shorter? I forgot this important word. Release. When you fall, you release lots of energy. And when you jump up, you absorb lots of energy. But if I'm this electron here and I jump up here, I'm going to absorb little energy. So a big change takes big energy. A little change takes little energy. Light is just a small part of the electromagnetic spectrum. So we showed this, and this is the little wedge of visible light. Okay, the little wedge of visible light. Now notice this is visible right here. Tinka, 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 tinka. Okay, so in this little wavelength section right here. Look at all the stuff that's bigger than that, all the stuff that's smaller than that. Okay, so light is just a small part. So, and notice it's kind of middle-ish. The lowest energy ones and the lowest energy and the longest wavelength are radio waves. So in order of the ones you need to know, sadly you need to know this, but I'll put it in just so you know it's going to pop up right here. So radio waves, not scary, low energy, not anything we need to worry about too much. But what's weird is we think of microwaves as being, ooh, look out for the microwaves. They are also low-ish. Right? Radio is lowest. Microwaves are low-ish. Okay, and notice radios show up in this. Okay. People in light bulbs. So here we get light. So we have radio waves. We have microwaves. We have infrared. So the next ones that pop up are infrared. We have a little bit of visible. We have UV, which is ultraviolet. We have X-rays. X-rays. And then we have gamma rays. So this stuff is dangerous. This stuff is not very dangerous. And by the way, we're being bombarded with radio waves all the time. How we know this is we can turn on a radio and we get radio signals. Woo! You need to know these in order. You need to know that which one has the longest wavelength, which one has the least, and which one has the shortest wavelength, which has the least energy and most energy. So we have to learn these in order. So I'm just going to read them to you 5 or 6 times. Radio, microwave, infrared, visible, ultraviolet, X-ray, gamma. 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 Now I want you to say them in like you're a little kid voice. Okay, let's try it.
Radio, microwave, infrared, visible, ultraviolet, X-ray, gamma.
One more time. Radio, microwave, infrared, visible, ultraviolet, X-ray, gamma. Good. We are done. Review. Spectroscopy is a branch of science concerned with the investigation and measurement of spectral procedure when matter interacts with or emits electromagnetic radiation. Know your equations. Woohoo, that's a lambda. Vocab. Waves, crest, wavelength, medium, photon, quantum. Falling electrons release photons. Rising electrons absorb photons. And we now know the Magnificent Seven. Radio, microwaves, infrared, visible, ultraviolet, X-ray, gamma. Toodles.